All right, let's talk about something every engineer has probably dealt with, that one motor that just keeps tripping its breaker every time you try to start it up. It's so frustrating, right? Well, today we're going to dive deep into the IEC standards to figure out exactly how to size motor circuits. The goal? To make sure your designs are not just safe and reliable, but completely free from those annoying nuisance trips.
So here's what we're going to cover. First, we'll look at the motor's inrush challenge. Then, we'll walk through the IEC sizing procedure step by step. After that, we'll get into choosing the right trip curve. This is super important. We'll also do a quick comparison of breakers versus fuses, and finally, wrap up with the essential final protection checks. Let's get into it.
All right, first things first. We need to really understand the unique challenge that motors throw at our protection devices. This is a classic problem in electrical engineering. And honestly, getting this part right is absolutely fundamental if you want a system that's actually reliable. So have you ever had this happen? You hit the start button, you hear that little whir for maybe half a second, and then click. Silence. The breaker tripped. Again. It's not a fault, so what's going on? What's actually happening here? Well, the answer has everything to do with something called inrush current. Okay, so what is inrush current? Well, when a motor first starts up, for just a moment, it acts kind of like a transformer with its secondary shorted out. What that means is it draws this massive spike of current. We're talking 5, 10, sometimes even more times its normal running current. Now, your standard circuit breaker sees this huge sudden spike and thinks, whoa, short circuit, and it does its job. It trips to protect everything. But here's the kicker. For a motor, that giant spike is completely normal.
So, if that's normal, how in the world do we solve this problem? Thankfully, we don't have to guess. The IEC gives us a really clear step-by-step procedure to follow. It lets us pick a protection device that's smart enough to ignore that temporary inrush, but will still do its job and protect against real overloads and short circuits.
And at the heart of all IEC sizing is this one super simple but absolutely crucial principle. The nominal current of your breaker, we call that in, has to be greater than the design current of your load, which for us is the motor, and we call that IB. That's it. This is the starting point for everything that follows.
This whole thing boils down to a really straightforward 3-step process. Ready? Step 1, we calculate the motor's actual running current. Step 2, we pick a breaker with a rating just a little bit higher than that number. And step 3, and I can't stress this enough, this is the most critical part for motors, we select the correct trip curve.
So let's look at step 1. This is all about the motor itself. That design current, our IB, is just its full load current. All you have to do is grab the motor's nameplate data. You'll use the good old power formula, but just make sure you account for the voltage, the power factor, and the motor's efficiency. That's how you get the real, true input current. Okay, now we're at the most important part. I kind of think of this as the secret sauce for motor protection. We're talking about the trip curve. This little detail defines exactly how a breaker responds to high currents, and it's what makes it possible to tell the difference between a totally harmless startup spike and a genuinely dangerous fault. So, let's break down this table because it lays out our options perfectly. You see that type B breaker? It trips at about 3 to 5 times its rating. That's fine for simple stuff like heaters, but it's a big no-no for motors. It's almost guaranteed to cause nuisance trips. That's why for motors, we're looking at type C and type D. A type C can handle a spike of 5 to 10 times its rating, so it's usually good for smaller motors. But for those really big, beefy industrial motors, you gotta go with a type D. It's designed to hang on all the way up to 20 times its rating, which gives that motor all the time it needs to get up to speed.
And this really drives home the main point. Listen, you can get the amperage rating perfectly right, but if you pick the wrong trip curve, your system is just going to be unreliable. It's that simple. The curve has to match the characteristics of your load, period.
Now, of course, circuit breakers aren't the only game in town. Fuses are the classic, tried-and-true solution for short circuit protection, especially in motor circuits. They're super effective. But the question is, how do they really stack up against a modern molded case circuit breaker, an MCCB? Okay, this comparison is really important. Look at the MCCB, specifically a motor protection circuit breaker, or MPCB. It's an all-in-one deal. It gives you both short circuit and overload protection in a single device. Now look at the fuse. A Class AM motor protection fuse is different. It's designed for one thing and one thing only, short circuit protection. It provides zero protection against smaller, long-term overloads. So, and this is the critical takeaway, if you use an AM fuse, you absolutely must pair it with a separate thermal overload relay. It's not optional. All right, so let's say you've done the work. You've calculated your current, you've picked your breaker type, and you've chosen the perfect curve. You might think you're done, right? Well, not quite. We're almost there, but we cannot forget the final verification steps. This is what makes sure the entire system is not just robust, but also fully compliant. So there are 3 last things to check. Check number 1, short circuit capacity. You need to make sure your breaker's breaking capacity, its IC, is higher than the worst-case fault current you could possibly see. Makes sense, right? Check number 2, cable protection. Your cable's capacity, IZ, has to be bigger than your breaker's rating, IN. Why? Because the breaker's there to protect the cable. And finally, check number 3, overload setting. If you're using a separate overload relay, you've got to double-check that it's set correctly, usually between 1.05 and 1.2 times the motor's design current. This is what protects the motor itself from slowly burning out. And that's it. With those final checks, we've really walked through the whole process for correctly sizing your motor's protective device. But it's so important to remember that the breaker or the fuse, that's just one piece of the puzzle. And that leaves us with one last really critical question to think about. How do you verify that the cable itself can handle the massive energy from a short circuit before that device even has time to trip? Well, that's a whole other layer of analysis. But for now, you've got the tools you need to select the right protection. Thanks for tuning in.